Good afternoon, everyone. I'm Nancy Molenda, Director of Communications for the Aluminum Extruders Council. Oh, that's still on hold. Okay, hold on. Where's star one? On the phone?
The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone. I'm Nancy Molenda, Director of Communications for the Aluminum Extruders Council. I'd like to welcome you to our webinar, Leveraging Aluminum Extrusion's Attributes for Effective Building Solutions. All computer, audio, and telephone lines are muted, so if you have a question during the webinar, please select Q&A or chat from the toolbar. Type your question in the dialog box, and our presenters will be able to address your question at the end of the presentation if there's enough time. If you plan on submitting for AIA credit, you must be logged into the webinar individually and attend for the entire session. No partial credit is awarded. Credits earned on completion of this course will be reported to AIA CES for AIA members. Certificates of completion for both AIA members and non-AIA members are available upon request. Today's presentation is in two sections. In the first, we'll show you how the extrusion process and the attributes of aluminum extrusion combine to create powerful product solutions. Then we'll show you how to move from an idea to those solutions. At the end of the course, participants will be able to state the attributes of aluminum in extrusion-based product solutions, recognize the contribution of fabrication and finishing to aluminum extrusion product solutions, identify how alloy selection and part geometry combine for effective product solutions, and understand the economics of initial costs and long-term savings of extrusion-based solutions. Our speakers today are Louis Smith, President of Jordan Aluminum Extrusions in Memphis, Tennessee, and Shane Seaver, Vice President of Sierra Aluminum Company in Riverside, California. Both gentlemen have experience in producing aluminum extrusions for the building and construction industry. I will now turn the webinar over to Louis and Shane. Louis will be our first speaker. Louis?
Thank you, Nancy. So, my name is Louis Smith. Shane will be taking the second half of the presentation. I'll cover the first half and talk about some basic advantages of aluminum and the extrusion process, and then talk about finishing for a bit, and then kick it over to Shane to cover the remaining points we want to make today. These first few slides, I want to get the creative juices flowing and just show some examples to give everybody an idea of what can be created with aluminum extrusions before we jump into some of the processes. On this slide, just showing you, looking at the middle top, showing a heat sink and a mount for an LED light fixture, and we'll talk about more about that later. Moving to the right, showing a commercial window framing with a thermal barrier to break up the conductivity, and we'll talk about that as well more in the slides. And on the bottom, moving left to right, is a housing for an oxygen concentrator. In the middle is a helix, which is used as an impeller in an auto supercharger. And on the bottom is a heat sink and mount, or excuse me, a housing, a heat sink for a fan. Okay, next slide, please. So on this slide, on the top left, we show an interior light LED light fixture. In the top right, a radiation therapy unit, which is using extruded aluminum components to form the shutter controlling dosage, and there's some more information about that on the AEC website, but it's an example of a part that used to be all steel that was converted to aluminum for some of the attributes that we'll cover here in a few minutes. On the bottom left is a kitchen casework system utilizing extruded framing, and on the bottom right, building and construction application, some light shelves for commercial windows bouncing natural light into a room. for energy savings. You see this a lot in LEED buildings. Okay, next slide, please. And just a few more examples before we jump into some other items. On the upper left is an HID light fixture for medical operating suites. On the upper right, Tesla Model S, which employs over 25 separate aluminum extrusions. And the bottom left is the Apple Watch Sport Edition, which employs an extruded and anodized aluminum case. And on the lower right is an extruded decorative scene outside a baseball park in El Paso, which takes advantage of some of the fabrication properties of aluminum. And we'll talk about all these, like I said, as we get into the presentation. Next slide, please. So on to the process, starting with the basics. This slide is pretty simple. You heat aluminum alloy or billet. You push it through a steel die, and it comes out in the shape that you desire. Shane will talk more about design and what shapes work better and when, but just the point of this slide, just wanted to show basics of how to do aluminum. We've got a few more slides about aluminum, basics of aluminum extrusion. Next slide, please. So here's an example. One of the common questions we get in the extrusion industry is how do you make a hollow die? So for this example, we show how that's done. Note how the Play-Doh can flow through the opening between the part of the die that forms the outside diameter and the inside mandrel that's supported by two horizontal supports. You can see in the top right-hand corner those horizontal supports. The Play-Doh, just like aluminum, welds back together due to the pressure needed to make it flow through the openings in the tube. So when we have visitors who've never seen an extrusion plant before, way we describe it is it's just like the Play-Doh machine you used when you were young. Next slide, please. This shows a little bit more detail about the first two slides that we showed regarding the basics, but basically aluminum is heated in the furnace to a malleable temperature anywhere from 750 to 90 degrees. It's inserted into the extrusion press with the die on the end. It's pushed with a huge hydraulic ram. It could be pushed out anywhere between 100 and 300 feet. The aluminum is then sawed. It's stretched to get back its tolerances and its original shape properties. The aluminum is then cut again to fit in the aging oven, anywhere from 8 to 25, 30 feet. And at that point, it's artificially aged to get back to its original hardness properties. Okay, next slide, please. Okay, so this is a good slide to just describe the basics attributes of aluminum and the basic attributes of extrusion. And we're not going to cover all these obviously today, but we are going to cover 4 topics from each. And I believe if you go to the next slide, it's got those highlighted. Thank you. So we're going to cover just quickly some brief examples of a high strength to weight ratio of aluminum, its corrosion resistant properties, its heat conductive properties, and the fact that it's fully recyclable. And then shifting gears to extrusion, we're going to talk about how it's suitable for complex integral shapes, how that saves product manufacturers money. It's attractive, it's got a wide range of finishes, it's easy to fabricate, and short production lead times and cost effective. Okay, next slide, please. So the first attribute we want to cover is the high strength to weight ratio. And this slide basically shows a graphical representation of aluminum compared to steel. This is a mild steel compared with a 6082 alloy. Shane will talk more about alloys in the second part of the presentation, but the basic point we want to make here is aluminum is very similar in terms of tensile, and a third of the density. So the slide on the left shows the tensile, and the slide on the right shows the density of aluminum versus steel. Next slide, please. So I know we've got the audience is the AIA group, but we thought it'd be relevant to point out how this high strength to weight ratio has been noticed in other industries, and in particular in the automotive structure. And you see two really good examples here: the Ford F-150 and the Corvette. Both of these cars have have reduced their dependence on steel in order to lighten the vehicles, yet maintain the strength. The EPA has come out with CAFE standards that must be met, and so cars are trying to reduce weight and maintain strength, and aluminum is increasingly the material of choice. Next slide, please. Here are some examples from the building and construction world. On the left, an extruded canopy incorporating PV panels, which provide shade under the canopy and provide power through the PV panels. This is from the Salt Lake City Public Safety Building, which is a LEED Platinum. In the middle is a skylight extruded aluminum window framing, very open space, very airy. And on the right is an extrusion-based facade, the Anaheim Regional Transportation Intermodal Center. And again, all these applications show the high strength to weight ratio used in the building and construction application. Next slide, please. Here's another one from the transportation world, and this is a rapid deployment military bridge. And so the U.S. government designed this, and basically this is a bridge that you can manually put together, and they use it to drive small vehicles across, and aluminum was selected because it could hold the strength to support those vehicles. Next slide, please. Okay, moving on to the second characteristic of aluminum. It is corrosion resistant. Aluminum does not rust when it's exposed to air. Aluminum reacts with oxygen to form a thin oxide layer that is both durable and corrosion resistant. Properly alloyed and finished, aluminum can resist corrosion by salt water and various other chemicals and materials. We'll talk more about finishing in a minute, but next slide, please. Here's a good example of corrosion resistant. This is a floating structure for oil sands tailing pond, and this example is meant to show aluminum being the material of choice in pretty much as nasty of environment as you can find a tailing pond. Tailing ponds are difficult environmental challenge for the oil and gas industry, because it basically is what's left over after the oil is extracted. So it contains salts, acids, hydrogen sulfide, really nasty stuff. And that industry selected aluminum because it creates its own protective surface. On the left, you see a floating dock under construction in the shop, and on the right is a close-up of the barge. Next slide, please. So moving on to the third characteristic, aluminum is heat conductive, and so it's widely used to transfer heat for both cooling and heating applications. On a weight to cost basis, no other material conducts better, and that's what these graphs are showing: the thermal conductivity on the left, the density, their weight in the middle, and then the bang for your buck. It's basically looking on a dollar per pound basis of these different, or a dollar per cubic inch basis of these different materials, and you can see aluminum clearly comes out on top. Next slide, please. So we'll go through a few examples on the heat conductive properties of aluminum. And here you can see an additional heat sink examples that illustrate the conductive nature of aluminum. We'll talk about heat sinks a little bit more in a second, but it's worth noting, of course, that with the building envelope, conductivity can create challenges, and we'll talk about those today and what in aluminum in our response to that. Next slide, please. Okay, here's another heat sink for a commercial LED light fixture. And an LED lighting has grown rapidly over the last few years due to savings in energy use and maintenance. And aluminum extrusions incorporate cooling fins that you see on the bottom right-hand side, wings that act as an integrated heat sink to dissipate heat from the LED light. The cooler the LEDs run, the longer the life, helping LEDs significantly outperform incandescent and fluorescent lampings, which is one of the main reasons why aluminum has been the material of choice for that industry. Next slide, please. Okay, back to the building and construction world. Here's an example of a building envelope. We saw this from the first few slides of a thermally broken aluminum extrusion. The break that you see basically prevents the transfer of weather conditions from passing through the aluminum. Next, I think we've got one more picture to show there, Nancy. Thank you. On the right, we show resulting U factors from non-thermally improved single cavity thermal barrier and dual cavity thermal barrier. And at the top is the non-thermal, and then moving down to the dual cavity. And basically, the point here is the U factor improves from 3.57 to 1.87 with the dual cavity. U factor is basically just a measurement for the rate of heat loss in a window assembly. So the lower the U factor, the greater the window's resistance to heat flow and better insulating properties. So while aluminum is heat conductive, there are solutions that make it applicable, of course, to the building and construction market. Next slide, please. Here's another example of aluminum's heat conductive nature. This is a 90-minute fire door that is getting tested. And when you test fire doors, you spray really hot material on it and see if it falls off the hinges. And aluminum, this technology is using thermal break material to basically keep the door in place so that it can pass the 90-minute fire rated test. I don't think this product is out in the market yet, but the point is we wanted to show how the thermal technology of aluminum can make the heat not continue through the aluminum. Next slide, please. Okay, so moving on to extrusions and the complex integral shapes that are possible. Shane will talk more about specific basic do's and don'ts with regard to designing aluminum profiles. But here you can see a very complex design that's made of two extrusions that with other material would probably be far more parts. You see all the detail around. No other process allows the designer more flexibility in combining form and function through complex integral shapes. Aluminum extrusions deliver economical, highly precise shapes that would otherwise be difficult to produce with the same number of parts in a different way. So next slide, please. So here's another example of a complex shape. This is again showing the thermal barrier with a concealed mechanical lock to hold the glass frame in place. Next slide, please. Here's another example of a complex integral shape. This is an adjustable support beam, and you can see how challenging this shape is. But I think the primary point here is that over distances of up to even 9 feet, this shape is able to hold its form while still performing the function of having a up to 400 pounds in patient weight, and this is a 6005 alloy. Next slide, please. So we talked a little bit about the automotive industry, and this is a good example of the automotive industry and their engineers taking a really hard look at taking advantage of aluminum extrusion's ability to make complex shapes and basically reducing weight and reducing the number of parts and saving money. This is a panoramic automatic sunroof, and you can see here that it basically consists of 6 pieces only, 2 extrusions and 4 small aluminum stampings, whereas it used to be a 28-part steel mechanism. So aluminum's flexibility and ability to create these complex shapes have resulted in reduced labor cost, a 20% weight savings, and a 22-part reduction. Next slide, please. And here's an example from the building and construction world. These are reed-like extrusions, basically serving as sunshades. Both of these pictures are from the same building. One's just shown vertical and the other horizontally. But these are sunshades comprised of an extruded aluminum components on the building's exterior and serving 2 main purposes: to block excess sunlight and reduce solar heat gain. Next slide, please. So we talked a little, we're going to touch on finishes. We don't have a whole lot of time to go into great detail, but basically aluminum accepts a wide variety of finishes. Briefly, paint, anodize, mechanical, and applique. Some terms that you're probably familiar with on paint. I think you can go to the next slide. Our AMA standards 2603, 2604, and 2605, and suggested uses. I'm just looking at that line item, but basically 2605 is exterior high performance type of applications, and 2603 is interior type of applications, and 2604 is somewhere in the middle, commercial light industrial. Next slide, please. On anodizing, you can see a range of dyed anodized products here. Anodizing doesn't just have to be clear, bronze, or black. You can do lots of different colors. Some terms to be familiar with in anodizing: architectural class 2 and architectural class 1 simply refers to the thickness of the coating. So architectural class 2 is 0.4 to 0.7 mils, and architectural class 1 is 0.7 mils or thicker. Primarily architectural class 2 used in outdoor applications, and class 1 typically in interior applications. Next slide, please. Here we just show the flexibility of paint to match colors, and so this is you can see custom colors were required to match a high-end retail and hospitality market, and you can match virtually any custom color with the painting process. Next slide, please. So here's an example of an extruded aluminum finish shown to look like wood grain. So there's lots of flexibility around even these types of finishes. Next slide, please. So another attribute we'll cover is the fact that aluminum is easy to fabricate. Machining, forming, joining are very doable with aluminum. Here we show a fence. This was on one of the first few slides too. It's milled out so pedestrians can see through it. The architect had in mind to simulate back in the old days, kids looking through knot holes in a wooden fence at a ballpark, And so it just shows the flexibility of aluminum with regard to accomplishing basically anything you want to do from a fabrication standpoint. Next slide, please. So in addition to all the characteristics we discussed, aluminum is, in order to make an extrusion, is relatively inexpensive, and you can do it quickly. And so those are the 2 points we wanted to hammer home, is that it's cost-effective and time-effective. On the left, we show aluminum extrusions, tooling costs relative to other processes, and you can see it's vastly more affordable. And these are for custom aluminum extrusions. And then on the right, we show the typical tooling lead time to get your custom aluminum extruder, bring in the tooling into to start producing parts. Next slide, please. Okay, so aluminum, of course, is sustainable and fully recyclable. Something like 70 to 75% of all aluminum ever produced is still in production today. In response to LEED version 4.0, as well as some other end markets requesting more granular information, the Aluminum Extruder Council is in the process of generating a new EPD, which is set for release this fall. And this is, we're excited about it. It'll have the largest cross-section from the aluminum extrusion market ever, and it'll be updating the current EPD that the Aluminum Association has had, but with more detailed information and more production included. So look out for that this fall. Next slide, please. Okay, so I think that concludes my part, and I will pass it on to Shane. Shane, are you there?
I'm here.
All right,
Louis.
sir. You got it from here.
Okay. Continuing on with what Louis started with, this next section kind of breaks into two sections. First section deals with alloy selection, shape geometries, and a little bit of fabrication. And then the second one deals a little bit more with economics and has a couple of case studies. So taking us back to a kind of a higher level view. Next slide, please. When we talk about aluminum, in and of itself is not particularly strong. But with a little bit of alloying material added into it, it develops quite a bit of different characteristics. In terms of alloys, as of June of 2016, there were 537 alloys registered in several different series of alloys. Each one of these goes with a particular application. Next slide. So within that, a little more detail. You have 1000 series, good corrosion resistance, good electrical conductivity, and good to work with. 1000 series is generally very lightly alloyed, and going back to the extrusion process itself, to try and get aluminum to behave like a liquid, to flow, light alloying is important. So in terms of this, when you get into some very complex shapes, heat sinks specifically, a lot of the very complex ones are made out of the 1000 series alloys. Copper, the 2000 series, really out of the scope of this presentation, but that is for aircraft. 3000 series is a good formability extrusion alloy, though not used very much for the building industry. 4000 series, not available as extrusions at all. 5000 series, it's a nice alloy, alloyed with magnesium, has moderate strength, but where it really shines is in marine corrosion resistance. So in a marine environment, you're typically dealing with salts, humidity, pitting corrosion. This alloy withstands that fairly well. 6000 series, which is the broadest available alloy. It's alloyed with magnesium silicon. It's really kind of the garden variety alloy. It's got good strength, got good corrosion resistance. It's well formable. It's not the best for any one particular application, but it's got the broadest applicability. And finally, 7000 series zinc, very poor corrosion resistance. Once again, it's a high-strength alloy used for aircraft. Next slide. Now, looking within the 6000 series family, and this is, like I said, kind of garden variety alloys, and certainly alloys that are most used in the architectural industry. There are kind of 5 main alloys that are out there, basically increasing portions of silicon, increasing portions of magnesium. The lower alloy the material is, the easier it is to extrude. So if you have shapes that are more complicated, an alloy like 6063 is appropriate. You can fill in the voids well. If you need something that isn't quite as detailed, needs to be a little stronger, but still have some detail, the 6005A alloy is a very nice alloy to use. Old reliable structural alloy known in the industry for decades, 6061 has even more magnesium and silicon. And finally, a relatively new alloy, which is really gaining a lot of traction in the automotive areas, the 6082. Balanced alloy, fairly even proportions of silicon and magnesium, but it's very strong. Not necessarily appropriate for architectural industry, but certainly is gaining a lot of strides in the automotive. Next slide. So at least within this, and this is what's key when you really come down to a design perspective, is the easier something is to extrude, the cheaper it's going to be. The extrusion industry, it's fairly high overhead business, fairly high labor cost business, and most extruders tend to live in the world of pounds per hour. And so if you have a shape, at least on this graph, we have something defined on here, really a dimensionless unit called the extrudability index, and 6063 and 6060 are always defined as kind of the 100 on there. It's nicely running whatever. If you have a shape that runs at that 100 index, let's say 1,000 pounds an hour, and you want to substitute it to a 6005A, which only runs 70% as fast, you're only going to get 700 pounds an hour. Well, you have costs that you have to amortize over less production. It's naturally more expensive. You can get something for that. It's a stronger alloy, but you just have to keep in mind that those particular things will work against you in your design. It will cost you more money to go to a higher strength alloy. But you can also see how the alloys compare in terms of their strengths. The alloys itself compared to mild steel on both the tensile and yield strengths. Next slide. Within the heat-treatable alloys, there's also various tempers that can be done in there. And tempers are basically you're heating the metal up so that on a molecular level you're starting to displace the atomic matrix a little bit, and by growing some of these alloys or these elements inside the alloys to a form that's a little larger, you get more strength. And so within this, there's several different tempers. F temper is kind of, you get what you get, you extrude it, you cool it a little bit. There's really no properties that go with it. Annealing it, you're heating it up at a very high temperature for a certain period of time. You're almost essentially overaging it, but you're getting it to the point where it's very easy to form. It's very ductile. So if you have shapes that you need to, things that you need to bend, things you need to shape, it's a good thing to do. H1112 really not applicable for this discussion. It's not applicable for 6000 series. T1 temper, it's very good for bending applications. So if you have radius windows, especially large, generally very large radius windows in commercial buildings, libraries, things like that, T1 temper is a good place to start with that. Though the material will artificially age over time, so you want to make sure you have fairly new material out of the manufacturing facility within a couple of weeks. Otherwise, through the natural aging process, you won't be able to bend it as well. T4, it's cooled at a minimum cooling rate, but then allowed to artificially or naturally age, generally not used in the architectural. T5 and T6 tempers are generally what's used in the architectural industry. Just one is cooled and one is solution treated, which is basically a combination of cooling rates and the exit temperatures. But those particular tempers give you your best strengths. Next page. So within the geometry itself, there are three general geometries. There's three general terms that we use to describe shapes. We have solid shapes, which, as demonstrated up there, There's no cavities, there's no voids in it. It's just a nice open shape. Flat plate bars, rods, those would all be solids. And then you get into some angles, some tees, other things like that, all basic solids. Semi-hollows. While not quite a fully enclosed area, you have a hollow area in there that has a very small tie-in to the exterior of the shape. There are two types within the semi-hollow consideration. There's a Class 1 and a Class 2. Class 1, real simple, it just means it's a balanced semi-hollow. You can see all the wall thicknesses are consistent. The semi-hollows are the same size. Within the Class 2, it typically means that you've got an offset in there. You've got a dissimilar wall, dissimilar thicknesses. You can see on this, the left wall is thicker than the right wall, and both the left and right wall are thicker than the bottom and top walls. So it's basically an unbalanced shape. And then finally, within the hollow categories, there's three different classes. Class 1 is generally going back to symmetry. It's a balanced shape. Class 2, it's generally something that isn't quite as balanced, or a single hollow within a larger shape. And then finally, Class 3, you're getting into complex hollows, typically a shape with more than one hollow, things that are a little more unusual, things that are a little harder to run. Next slide. Now, Louis already showed you this particular shape, and this is something that, obviously we would never see a customer that would probably give us something that would look like this, but it's an example of everything that's here. You have, in terms of doing an assembly, you have a hinge detail with a snap fit, so you can key two pieces together, they will hinge together, they will snap in place. It shows you some heat sinks, some grooves that can accept things, some surfaces, fluted surfaces for hiding details. Slots for receiving nuts, grooves for receiving screws, just all the different things that you can do in a shape. Next slide. Now, in terms of general design practices, symmetry and uniformity are oftentimes the key. And so if we start kind of top left corner, uniformity, you can see we've got two examples of the shape on the left. We've got shapes, and for all intents and purposes, they look very similar. But the shape on the left, the walls are thicker than I guess the base of the shape is. And so you've got some dissimilar flows. Might slow the extrusion down a little bit. So the shape that's adjacent to that, you can see the wall thicknesses are very similar all the way through. And the next shape, just barely to the right of that, is hollow. You can see the two versions. The one hollow, you have a very thin wall in the middle with the red circle. That very, very hard detail to manage versus the one on the right. It's very much the balanced shape, balanced wall thicknesses. Things will flow better. Next one, symmetry. You have parts, instead of having one part, we'll often build two-hole dies so that we can balance the flow within a dissimilar shape so things flow easier. The bottom left, smooth transitions. This one's kind of near and dear to my heart. I'm involved in a lot of finishing, and not so much on the inside angle, but the outside of the part. On this one, we're showing sharp corners. Don't put sharp corners on parts. Sharp corners lead to slow extrusions. It's very hard to get the metal to fill into the corner. But then likewise, when you get to a secondary operation like finishing, specifically painting, if you can the best analogy I make is that if you try to paint a sharp corner, it's like trying to paint the edge of a knife. Paint doesn't stick to it very well. So, consumers bumping into it, knocking it, even through the fabrication process, it's hard to keep paint on a sharp corner. Plus, it usually costs more. You burn up dies. It's harder to do. So the example is more of a U shape. Round those corners out, things flow better. It actually maintains the integrity of your finishing a little better. Same thing on the shape adjacent to that. You've got some hard transitions. You kind of come into that bottom circle. You almost have a very sharp tip on that. That's going to be an area where you're going to get a lot of erosion on the tool. Your tool life will be very much diminished. Obviously, we amortize tool life into pounds, so the faster we burn up our tools, the more your parts cost to make. So smooth is always good. And then finally, the enhanced visual surfaces. On this one, you have some little screw bosses that are basically integrated into the part. Any place where you have a screw boss, an angle that comes together with a flat surface, you always generate more friction in the areas where angles come together than you do in flat areas, and that friction leads to a difference in grain structure, which, especially in things like anodizing, leads to a different anodizing response. So you'll see sometimes some ghosting, some transfer marks, lines in the middle of shape. One of the ways to deal with that is to basically put just some little bitty grooves adjacent to those areas to take the consumer's eyes away from those potential, I wouldn't say defect, I always call them character areas, but to give it a little less character, make it a little bit more visually appealing, give it some little fluting on there to kind of enhance that. Next slide. Screw bosses are very easy to incorporate into extrusions. You know, self-tapping screws, thread cutting screws, very easy to integrate into it. The example top right shows the same, basically the same thing getting accomplished as the one on the bottom right, but from an economic perspective, the one on the top is going to extrude faster. It's also going to have a much lower cost tool to make that shape, versus the one on the bottom. There's more metal in it, and it's going to extrude slower. So costs are going to increase. In certain situations, you may need all that additional strength and all that additional material to do it, but other situations you may not. So better to work with your extruder and try to come to that happy medium to get you the best price extrusion for your need. Next slide. This is an example of some hollow-shaped dies. In terms of this, generally speaking, rule of thumb, the less hollows you have in a shape, the better. And so shape on the left, it's essentially a single void hollow. There are some little semi-hollow sections in there, but much easier to keep that tool and to keep that shape flowing and uniform on a runout table than the one on the right, which has the triple void hollow in it. Same kind of deal with the pair of shapes on the right, making it into a single void hollow with two semi-hollows versus two hollows and two semi-hollows. Once again, easier to maintain. And obviously, playing with your AutoCAD programs, running a moment of inertia calculation on it, you can get same type of bending deflection. There's just all kinds of things that you can do with geometry and aluminum because you have so much flexibility in your design. Next slide, please. This one's kind of really out of the realm of architectural, more of an electronic perspective. And from an extrusion perspective, myself as an extruder, this isn't a shape that we would really want to see, either one of these. Neither one of them are particularly wonderful. But when you're really coming down to economics on this and thinking about secondary operations and reducing material, shape on the right, even though it's a hollow shape, probably has a more expensive die. You've got much lower tongue ratios on this. You have some screw bosses in there to screw some material in. You have some hollow shapes that are put in here to reduce the amount of material. More than likely, this is a heat sink for an LED light fixture. It once again gives you an idea of some things that can be done to reduce costs. Next slide. Now this one is interesting assembly. You've got basically three pieces in this assembly. You've got a top plate, you've got kind of a U-shaped body, and then you've got an angle bracket. So at least in terms of this, the top plate, there are four screw holes that are fabricated into this. The body, for that top plate to go into that, you're going to have four vertical holes to go underneath the plate's hole. You've also got some horizontally drilled holes in there. And then finally, the angle on there, you've got four drilled holes on that angle, two from attachment and two to actually angle apart. Next slide, please. So this shows basically same extrusion or the same assembly, except converted into an extrusion. So at least in terms of this, you've gone from three pieces now down to two. The top lid has now been converted from basically a flat plate that had to be drilled in four locations to a hinge with only two locations on the right. There's also been a little bit of detail added in the to make it a little less, make it a little more attractive. In terms of the body shape, the U-shaped part, you can see on that where the hinge is on the left, you've eliminated the vertical drill holes, the pair of them. On the right, you've also put in basically a linear screw boss, and so you've got an area now where you can screw into that. So 4 vertical holes for fabrication have been eliminated. On the horizontal space, the 4 horizontal holes that were drilled in there have now also been eliminated. They were just incorporated into the shape in terms of a screw boss. And then finally, the kind of the flange angle piece on the side, that was also incorporated into the shape. You eliminated 2 fabrication holes in that, and you basically just maintain your anchoring. So you've reduced your machine operation, you've eliminated one piece, and you've got a part that's probably much easier to assemble, much easier to maintain. So moving on. Next slide, please. Standard tolerances. Now, once again, all of this stuff, we are trying to get aluminum to behave like a fluid. We are pushing a solid through a die. We have to worry about things like tolerances. And so things that we constantly worry about are cross-sectional areas, twists, straightness, flatness. Twist and straightness get to be especially important with long cut lengths, especially when you're getting into snap fittings and hinge settings, so we always want to be aware of that. When you talk about tolerances, there is a standard tolerance table. That is the next slide. We'll talk about that in just a minute. There's a standard tolerance table that all extrusions use that is published by the Aluminum Association. Those tolerances are fairly large. Most extruders can maintain tolerances better than those. 2/3 of the recommended numbers are a good place to start with the discussion, but your extruder does need tolerance. So the idea that you're going to get a part that's going to have no tolerance on it at all, it's going to be absolutely precise, that's not a good way to think about it. When you get into some simpler shapes, smaller shapes, you can even get to half a standard tolerance, but, there is going to be some variation, so you always want to take that into account in design. Getting your extruder involved up front so that they can tell you what they can do is very, very important in all of this. Next page. This just shows you an example of, basically shows you the tolerance table. Oh, go back one, please. Just the tolerance table, so you can see what that looks like, and it's very easy. You can get this straight from the Aluminum Association. It's called the Aluminum Standards and Data Table. Next. And so fabrication, assembly, extrusions can be machine formed, welded, assembled, all of that stuff. This shows just a couple different operations. Next slide. Okay, so this shows you how a part can essentially be built. So you're starting with an extrusion on the right, a single void hollow, basically cutting into short lengths. It gets punched, drilled. The ends get basically rounded off a little bit. A channel gets welded to the top surface of it. So you can see that gets built in the second step of that. It can get finished, whether it's powder coated, wet painting, anodizing. Anodizing is probably not a good thing to do in this because of the welding. Dissimilar elements, the heat of the welding process, you're going to have not a particularly wonderful anodized product, so powder coating or painting would be great on this. And then finally, you can see what the finished assembly is, some type of a stand. Next slide. Additional thing, high-end speaker enclosure. You're taking an extruder, and just a standard extrusion, fairly large extrusion, and drilling a couple of holes out, drilling some screws in there so that your speakers can mount in there. This can probably be painted, anodized, just kind of whatever look your customer's going for. Next slide. And then finally, just an additional thing, you can see in terms of this, you can take a part, is a very complicated part as far as the extrusion goes, but you can oftentimes get a part that has pretty much the correct dimensions on the exterior of it. Do some very light machine, you can get some hollows put into it right off the front, and then you can machine them out. There's a lot that can be done with extrusions, starting with a semi-custom base shape, and then doing the machining from there. Next slide. And so this one, now we're going to move into just some basic economics and some case studies. Next slide, please. So generally speaking, aluminum is generally always considered to be more costly than steel. And obviously on a weight basis, we've got some things cited in here, and granted they're a little out of date, and the market will have moved a little bit from here. But relatively speaking, carbon steel is cheaper than aluminum on a mass basis. This is cited $700 per metric ton compared to $1,800 per metric ton. But the thing that you got to keep in mind with aluminum is aluminum has a much lower density. You can do a lot of things with the shape because of the extrusion process. You can design in an awful lot of features that you can't do in steel because you can get aluminum to flow. And then it is very corrosion resistant. Not a lot of treatment has to be done, especially when you get to either corrosive environments, salty environments, coastal. It's very good. And then at the end of life, you actually have you have a value that you can harvest out of the aluminum. Not as much value can be harvested out of steel. Next slide. So this kind of gives you an idea. A statics lesson kind of goes outside the scope of this presentation, but essentially you've got a load. You've got a series of very common steel shapes with various flanges and webs and thicknesses and everything else. And then you've got a lot of density and weight in the steel. And so when you basically look at these couple of shapes as they're considered, you've got an I-beam, you've got a channel, you've got a cold form channel, you've got 39 pounds, 47 pounds, 30 pounds of steel, and you've got the various costs. You're trying to prevent a certain amount of deflection on this part. You can design in the same amount of deflection resistance with a substantially smaller amount of aluminum. And so even though the aluminum will in fact cost more on a mass basis, taking into account that you've only used a third of the material, you can actually come up with a part that is actually cheaper. And then you get the added attributes of it being more corrosion resistance. So you have a lot less that you may have to put on it in terms of coatings. Next slide. Case point on this, a pedestrian bridge. Looking at the total cost of ownership of a bridge, you have material and fabrication taken into account of this, alternative coatings for the steel, it's a 50-year life expectancy, end-of-life disposition value. And so, at least in terms of this case study, it's basically material, fabrication, coatings, not installation cost. Although in this particular case study, because you got a little more than half the weight than you would in the steel, bringing the material to the site probably costs you less with the aluminum than it would with the steel. And so essentially a bridge, 70 foot long, 6 foot wide, no coating on the aluminum, so mill finished, and a couple different coatings on the steel. Next slide. So total cost of ownership, initial material fabrication costs were higher with the aluminum than with the steel. The total cost of ownership for the aluminum bridge was 22% less than the least costly steel alternative. And once again, installation and would have further taken into account the advantages. And so, the aluminum costs you more up front, but essentially once you put it in place with the proper fasteners and everything else, you didn't have to do anything to maintain it. With the corrosion resistance of the bridge, you didn't have to do anything. The steel, coatings that you're going to put on there, you're not going to put a really high-end PVDF coating on a steel bridge. It's not hard enough. It won't handle the environment. It would abrade right off. So you're going to be using more along the lines of enamels, things like that. You're going to have to essentially treat that bridge a couple of times. You're going to have to do some maintenance. You're going to have to remove some rust. You're going to have to do some recoating periodically. Next slide. So I guess where this is really coming down to is extrusions can provide a great resource for your design. They're recyclable. It's sustainable. The design can be done quickly at minimal cost. There's a tremendous amount of resources available. Next slide. To really leverage the material itself, you have to take into account the alloys, the geometry, the fabrication you're going to do. You can reduce part counts. You can optimize performance. Your designs can get a bit more creative. You can easily machine cut, bend, fabricate, all of those kinds of things. Next slide. But this part right here, this is the most important thing. Get your extruder involved up front. In the design perspective of extrusions, our die shops, our engineering, We oftentimes have customers that bring us designs that they're wonderful. They do exactly what the customer wants. We just can't make them. And so if you have an idea, a napkin sketch, a pencil sketch, something up front, hey, this is what I'm thinking of, this is what I'd like to do, your extruder can, with very little time and very little effort, give you some tips to help you make your design up front. And then obviously any adjustments you make in your design through, using some of the modeling in AutoCAD, you can very easily see what the consequences of that are. But really by leveraging the geometry and leveraging the material, it really gives you some opportunities to do some things that you just simply can't do with steel. Next slide. And then finally, there's a number of additional resources. The Aluminum Extruders Council is a great place to go. There's always an introductory article on what's kind of going on in the industry. You can find extruders that talks about application, give you some design. There are some buyer's guides. There's a buyer's guide. There's an extrusion manual. Both of those are available for download off the website and give you a lot more detail give you a lot more details in terms of well beyond the scope of this presentation. Next slide. Next. Obviously a lot more technical, and when you're really getting into design, you have the Aluminum Design Manual, and that was published as of 2015, just been updated, has new standards in it. That's really the technical place where you want to go to really get into design aspects. Next slide. And once again, within the design manual, I won't go through them all, but stability, compression, flex, shear, combined forces, fatigue, fire conditions, it's all in there. Next. And then beyond the Extruders Council for the extrusion aspect of it, there's also the Anodizing Council, website anodizing.org for technical information on anodizing. Once again, great resource. And then you have AMA for basically where the standards are published, a little more information, verified components list, those kinds of things. And then next slide. Off the AEC's website, you have a lot of different people that you can talk to. And within the industry, we're always happy to share information, get into designs. We really want to help you. We want to partner with you. We want to help solve your problems in a timely manner. And get on down the road. So that's all I have. Nancy, I guess you can take it over from here if you'd like for questions, and we'll go from there.
All right. Thank you, Louis. Thank you, Shane. If anybody has any questions, please go ahead and put it in, type it into your question box, and we'll ask our presenters to answer your questions. So while we're waiting for questions, I just wanted to let you know that we have another webinar coming up in October. So mark the calendar, if you would, please, for October 12th at 2 p.m. Eastern. We're going to be presenting, it's going to be hosted by the Construction Specifications Institute, and it's a webinar that will outline the results of the aluminum extrusion industry environmental product declaration that Louis mentioned earlier in the presentation. The council will be revealing the data for two EPDs, one for thermally improved and one for unimproved. And the data collected will provide important information on recycled content and finishing mix and characteristics. The EPD will provide the most comprehensive information about environmental impact of North American aluminum extrusion to date. So watch for registration details on our website at aec.org. Thank our presenters, and I'd like to thank all of you for joining us today. Have a great rest of your day.